Greetings and welcome. How you guys doing today? We're going to start off with an example here. Of course related to how many, because we're talking about combinatorics, the study of kind of how many ways an event can occur. And today we're specifically talking about combinations. So, yeah, here we go. Let's just jump right into this. How many ways can a 5-card hand be drawn from a deck of 52? Of 52. So there's our question. So combinations are going to be different to us than permutations in one key way. And this problem is going to kind of reveal that. And what I want to point out about, right, if I draw cards from a deck of 52, I don't believe, well, I guess there's some games where maybe the order would matter. But assume that I just had like all of the hands drawn kind of simultaneously, right? I drew all the cards and then I put them into my hand and I looked at them, right? Now the order that I'm doing this wouldn't actually matter, right? Because like if I have like a straight flush, that's the same difference as like a straight flush where it was the same cards but in a different arrangement. I'm going to take those cards and put them back into the correct order, right? So like the order that I drew those cards actually doesn't matter to me. Just that I have those cards is what matters to me, right? So that's what we've got going on here. So order doesn't matter is the key idea here, right? Order doesn't matter. I mean, I suppose there are some games where drawing cards one at a time, right, could affect your play, right, like solitaire or something like that. But we're not considering that situation. So if order doesn't matter, let's first think about what if order did matter. Let's think about this as a permutation, right? If order did matter, if it did, this is what we would have done, right? We would have done a permutation of 52-5, right? Right? Or maybe you would have just said, tried to analyze this using like the little like hangman style approach, right? There's 52 cards for the first one, then 1 card less for the second one, 1 card less, and then 1 card less and 1 card less, right? So you could have multiplied that. That would have been considering, order mattering sort of thing. So let's actually look at this. Permutation 52-5, that would have been 52 factorial. Oh, gotta put a space between my dot and my exclamation line there. Over 52 minus 5 factorial in parentheses, right? Because that's a difference if I don't do that. So 52 minus 5 is going to be what factorial? Let's see, 47 factorial is it? So 52 factorial up top, I'll just write as 52 times 51 times 50 times 49 times 48 times 47, 46, 40, right? It would keep going, so why not just write that as 47 factorial conveniently? And you would have realized, aha, this could cancel out with that, right? So that's nice. And then I could multiply those all out and I'd get some big number. Let me tell you what that is. That would be, if order mattered, well, wrong color, here we go. That would have been equal to 311,875,200. So 311 million, right? So yeah, so that's if the order mattered. However, it doesn't matter. So let's consider how many extra we have. Now, I've got 5-card hands, right? So if I have like ace of diamonds, right? And then 4 other cards, right? I'd have to figure out, okay, I also could have had ace of diamonds here and that, and then I could also have had ace of diamonds here. Oh, that's a triangle. Let's see. Right? And I would have to consider like all of the different ways that this could occur, but not just for ace of diamonds, for every card. So how many extra ways is that? Right? This is how many ways can I arrange 5 objects 5 times, right? So that's going to be 5 factorial because it's permutation 5, 5. Right? How many different arrangements of 5 cards? Right, so that's permutation 5, 5, or 5 factorial, right? Which I believe is 120 or something like that. So that is how many times more I've counted than I need to have. So I'm going to actually want to divide by this number because I've overcounted significantly, all right? So what I would do is either I could have, had down in the denominator 5 factorial here, right? Or divide here by 120. And whichever of those I end up doing, I would end up with 2, 5, 9, 8, 9, 60. So 2.5 million, right? Way different than 300 million, right? In fact, it's different by a factor of 120. So, so that's what we'd have to consider. We want to eliminate those extra possibilities. So let's talk about combinations in general and see if we can figure out our formula. So a combination, all right, is the number of ways an event could happen in which order does not matter. So that's the key difference between permutations and combinations, right? Permutations, order mattered. Combinations, they do not. So let's see if we can think of some examples on the spot of what are some combination type examples where order doesn't matter. Selecting a team with no position or captains, or a group maybe, right? Let's see. Maybe, well, I was going to talk about CDs that you take on a road trip, but no one does that anymore. Those don't exist. I imagine road trips do, but you would just take like your phone or your MP3 player. Yeah, what's another thing where order doesn't matter? What can you guys think of? Right. Selecting maybe Skittles from the bag. Is Skittles spelled with a K? That feels weird. Yeah. Right, so like, when you grab a handful of Skittles, I'm assuming the order you did that didn't matter, right? Stuff like that. Pizza toppings, aha! But I actually had probably, maybe I'll avoid the P words because that makes me think about permutation. But anyways, you get the idea, right? Situations in which order did not matter. That's fine. Did not. I like it. So how about a formula for combination? All right. So so the combination of n objects taken r at a time is, and it's written as combo n comma r, and it's equal to, now let's actually see, it's going to be really similar to the permutation formula, right? So the permutation formula was n factorial, right, over n minus r, but I have to add this additional piece for combination. What number did this relate to? N or r? Right, that's related to the r, so I'm just going to have an extra r factorial in the denominator, right? And that's the only difference. So I'll write it for real down here. So this is going to be n factorial over n minus r factorial r factorial. Yeah, that'll do. So that's the idea. So let's do an example. Suppose there are 15 students, all right, and we're forming a 5-person committee. Let's see, do I just double every letter in the word committee? I like it. That's how I spell things. So how many 5-person committees can be formed from 15 students? So that would be a combination, because in a committee, you're all of equal authority. There's no position. So it would just be combo 15, 5. So that would be 15 factorial over 15 minus 5 factorial. Maybe you guys can start skipping the writing of the 15 minus 5 and just skip to just writing 10 factorial times 5 factorial. So notice by the dividing by extra 5 factorial here, there's going to be fewer outcomes than in a permutation, right? So that's going to equal, let's see, 10 factorial here. So that's 15 times 14 times 13 times 12 times 11 times 10 factorial over 15 minus 5, as I said, is 10 factorial. And 5 factorial, I'm actually going to write that one out this time. 5 times 4 times 3 times 2 times 1. And the times 1 you technically don't have to write. And let's see what we can cancel here. So 10 factorial and 10 factorial can cancel. I could cancel 5 times 3 is 15. Like that little trick. 4 cancels with 12, giving me 3. And 2 cancels with 14, giving me 7. So you wouldn't have to rewrite this, but I just want to point out what I have is 7 times 13 times 3 times 11. So sometimes being able to cancel stuff out, if you don't have a calculator or something, you could then more easily do some of this work out. 13 times 3 times 11 times 7, 3003. Man, palindromes today. Palindromes. 5 times 3 canceled with 15, yeah. Yep. So, all right, here's a follow-up question. All right, follow-up question. What if I had, I'll fit it here, part B. What if of those 15 students, let's say that 7 were boys and 8 were girls. All right, how many 5-person committees can be formed if I have 2 boy, 3 girl committees? All right, so we're not allowing a committee of all girls or all boys or 4 girls and 1 boy. I just want to figure out, okay, how many ways could this arrangement happen? And well, what we have here is kind of 2 separate problems. Now that my selection of 2 boys out of 7 is not affecting in any way my selection of 3 girls out of 8, right? So I actually have 2 independent situations here. So I'm going to kind of apply the basic counting principle, where I'm going to figure out my combo problem for boys, and I'll multiply it by the combo problem for girls. So for boys, I've got 7 and I'm choosing 2. And for girls, we have 8 and we're choosing 3. And because these were independent, I can just multiply them independently. So let's see. So this would be 7. I'm running out of room here. So 7 times 6 times 5 factorial over 7 minus 2 was 5 factorial. And r factorial is 2 factorial, so that's just multiplied by 2 times 1, or just 2. Let's see, for the girls one, 8 minus 3 is 5 factorial, so I'll have to go at least out to that. 8 times 7 times 6 times 5 factorial. 8 minus 3 is 5 factorial, and then the r factorial in the bottom is 3 times 2 times 1, or just 3 times 2. So let's cancel out what we can here. So for the boys, 5 factorial and 5 factorial. For the girls, 5 factorial, 5 factorial. For the girls, I see 3 times 2 is 6. And for the boys, I can cancel out that 2 with maybe that 6 a little bit and get 3. So I'm getting 7 times 3 times 8 times 7. Right? I don't think I missed anything. So I get 1,176 different groups. Right? So you can actually even have like cool little macro problems like this that have multiple combinations taking effect. Right? So, all right, thanks for watching, Internet friends. Hopefully you had a good time with combinations, and enjoy your palindromatic numbers for today. 3003. Bam.